Hello, continuing on with the 2022 Oxford PAT, we got up to question 13. Draw the functions that, and that on a common set of axes, label where they cross the axes. Right, so that's going to be mostly positive. Yeah, okay, we might want to fairly central. I don't think we've got anything leaning particularly one way or the other here. So x squared minus 1 is going to be doing that. We say label where they cross the axes, right? So that's at -1 and 1 and -1. 4x minus 2. Right, okay. So I'm going to end up drawing over some of my lines here probably. So let's label these. So that's y1. This is y2. So that is going to go through -2 there and a half there. Then we've got minus x over 2 minus 2. All right, that's going through here. So no, we're going to be all right. And that's meant to be a straight line. Let's get rid of that bit. So yeah, that's a straight line, just at a flatter gradient. It's going to be, yeah, it's going through -2. So that is all of that. Is that everything that we want? Oh, it's going to have another intersection, which I'm not going to be able to fit on the picture. Right, let's draw this again then. Now we know where everything is. It's going to be this one that's the pain. So we've got that going on, which goes through, what's that going to be, -4, because that will make 2 plus 2. So yeah, -4, that's at -2. You've got that steep line coming up here, which is cutting through a half. And then you've got the parabola, which is doing something like that. Okay, still a bit messy at -1 and 1. So we've got 1, 2, 3, 4, 5 intersection. Oh, and this one, 6 intersection points. Right, easier to draw on a bit of paper than it is on here, but that's fairly straightforward. Work out the x values of the intersection points. All right, okay. Right, yawn, yawn. So we've got, well, we've already got this one marked on here at -2. So let's label all of these. This is y1, that was y2, this is y3. So y2 and y3 intersect at x is 0, because we just want the x values. So that was that one. And then we've got no intersections between the y3 and y1. Is that definitely going to be the case? Yeah, it is definitely going to be the case. And then we've got 2 intersections between y1 and y2. So for y1 and y2, let's just, am I going to get scroll down on that? No, I'm not. So I'm going to have to write these down here. So y1 and y2, that means that we've got x squared minus 1 is equal to 4x minus 2. Now I can scroll down, and that's going to give us 2 positive values of x we're going to want on that. So x squared minus 4x plus 1 is 0. That's going to be, well, let's complete the square. X minus 2 squared equals 3. X equals 2 plus or minus root 3. So at least they're both positive. So that's our 1, 2, 3 intersection points. Okay. What is part B? C, I mean, that is part B done, yeah. Write down the single integral which describes a finite area bounded by 2 of the 3 functions. Do not need to evaluate the integral. Right, the only bounded area we've got is all of that. So, yeah. So let's go with that then. That is going to be, well, we've got an intersection point here. So that means we're going to have the, so we want to integrate the difference between these. That's 2 minus root 3. So we want to do, which one's going to be the higher one? Well, it doesn't really matter because we can do a mod of it anyway to get the area, but let's put the straight line. So we've got 4x minus 2 minus x squared minus 1 dx. So we're just taking the difference between them, going from 2 minus root 3 to 2 plus root 3. So that's what it's going to end up being. I suppose let's just simplify that down a little bit. because we can just say that the bracket then is going to be 4x minus 1 minus x squared dx to plus root 3 to minus root 3. I suppose some people might get worried about the fact that we're straddling the x-axis here. So we're taking the large one away from the small one. No, we're taking the small one away from the large one. Well, it depends which bit you're on. This is the trouble. If we're below the x-axis, so this bit here, we're going to get a more negative result for the quadratic because it's lower down. And then we're going to be actually taking off the, so if we add on something that's less negative, we're taking the more negative number, multiplying that by -1 to make it positive, and then taking off, because this will also be negative, a smaller amount. So we're still going to end up with a positive number below here and a positive number above. So when we add them up, everything comes out okay. Yeah, you could think of it as well of being, if we shifted both of the graphs up, we know that they're intersecting at some number here. So say, I don't know, say you just moved everything up 10, or even 1 would be enough to get everything to be positive. Then you're doing a +1 on there and a +1 on there just to shift everything up. You've still got the same area because you've just translated everything upwards, and then they're going to cancel out when you do the integral. So you don't have any worries about it straddling the x-axis. It's not like when we're doing an integral where you've got a single function that's doing, something like that maybe, and you want to get the total area, in which case you're going to get a positive bit there and a negative bit there, and they might start cancelling out. This is different on here for reasons already explained. So that's question 13, which seemed quite a nice straightforward one to get us going on the longer ones. Right, the Trojan asteroids share Jupiter's orbit around the Sun, approximately circular with a mean radius of 5.2 AU, where that's the astronomical unit defined there. The Trojans are clustered around 2 points labelled L4 and L5, where L4 is 60 degrees ahead of Jupiter in its orbit, L5 60 degrees behind. So if we've got Jupiter there, we're going to have L4 there and L5 there, where we've got 60 and 60 going on there, and that's all at 5.2 AU. Determine the mean distance between the asteroids, that one at L4 and that one at L5. So we've just got a triangle that's looking like this, of 5.2, 120, 5.2, and we want to get this distance here. I don't really want to do cosine rule, but we don't have to, because we can say that it's going to be 2 lots of 5.2 times sine of 60 degrees. So that's going to be 5.2 root 3 astronomical units. We don't need to change the unit. That's why we have AU, so we don't have to deal with meters all the time. Although I'm guessing we're going to have to turn it to meters in a minute, because that's why they've given it to us. A spacecraft travels in a straight line between the 2 asteroids, accelerating at 10 meters per second squared till the halfway point, then decelerating to the end. Okay, assuming the asteroids are approximately stationary on a time scale of the journey, neglecting any gravitational effects, find the travel time. Right, so we are going to want this then, because we're now dealing in meters. So sticking this in the calculator, just putting that in and multiplying it by the 1.5 times 10 to the 11 is giving me 1.35 times 10 to the 12 meters. Scroll down a little bit. So we're going, right, we've got that distance then of 1.35 times 10 to the 12. That's how far it's gone. So that must be our average velocity multiplied by our time. Our average velocity, so the change in the velocity is the accumulation of the acceleration, but that's over half of the time. That's our change in velocity, and the average velocity is going to be half the change in the velocity. So we need to do a half of the acceleration multiplied by half the time. The acceleration is 10, so we're going to have 10 over 4t is v bar. Okay, so we can just stick all of this in here. We've got 1.35 times 10 to the 12 is, actually I'm going to leave that as 10 over 4 because it's going to make things a little bit easier. we can take 10 off from both sides and then multiply by 4. So doubling it twice gives us 2.75.4 times 10 to the 11 is t squared. So let's make that 54 times 10 to the 10 because it makes it easier to square root. So t will be square root of 54 times 10 to the 5, which is 7.348. So 7.3 times 10 to the 5 seconds, which is whatever that is. Well, that'll do. I haven't asked for anything else. Explain why the assumption that the asteroids are approximately stationary during the journey is well justified. So we're going to have to say something then about how long the orbital period of Jupiter is going to be. So we know that we've got, let's just squeeze it on here. So Kepler's third law, we've got that t squared is proportional to r cubed. So if we've got that we can compare this to the Earth, this is going to be a constant. So 1 squared over 1 squared is what we're getting. So we're going to have that the orbital period of Jupiter is going to be something to do with 5.2 to the 3 over 2. Well, actually equal to that in years. So that is nearly 12 years. Nearly 12 years for Jupiter to orbit. So we've got 12 years versus this. So what would that be in days? So let's divide by 24, divide by 60, divide by 60. So 8.5 days, give or take. So we got 8.5 days versus 12 years. So 8.5 days is small compared to an orbital period of 12 years. So we can assume that they haven't moved very much. It is what we're going for on that last part. Yeah, that was a nice question. I like that. So that's question 14. Moving on. The projectile is launched at speed v, angle theta, as measured from the horizontal outwards from the top of a high cliff. Sketch the trajectory of the projectile for launch angles 5, 45 and 85 degrees. Use x as a function of t for the horizontal displacement and y for the vertical. Okay, fine. So how are we going to put all this down then? We've got y, we've got our x. Oh, blimey, we're going to have negative though, aren't we? Because we're on a big cliff. Right, I'm going to have to scroll down a bit more. So it was 5, 45 and 85. Right, the 45 one will be fine enough. Let's just draw that in, just doing standard parabola like that. So that's our 45 degrees. So if we're doing 5 degrees, it's not going to go as far on the range before it cuts the x-axis again, because you get maximum flat range at 45 degrees. So 5 degrees is going to be going a bit more like this. It's going to cross at some point. So that would be our 5 degrees. And then the 85 degrees. Right, now I've seen this sort of thing before as a heads up, and I'll show it in a minute, but I know that the 85 degree one is going to cross at the same as a 5 degree one. So hold that thought for the moment. It's going to go up a lot higher and it's going to go through there, and that's going to be another parabola. Right, so why is that the case? Why do these things cross? Like I say, this is not new to me, so potential advantage here. So let's write out our parametric equations for a projectile. So x is v cos theta times t, y is going to be v sine theta times t minus g over 2t squared. So I'm just doing suvat in both directions. You know, v is, s is ut plus half at squared. So we've got those, so we can rearrange the first one and then sub in for t on the bottom one. So we're going to get the y, because t is x over v cos theta. So we're going to get, that's going to be x tan theta. And then we're going to have a g over 2 multiplied by x squared over v squared cos squared theta. That gives us that. So this is what we've now got for our y as a function of x for a equation of a parabola, really, of a projectile. So y is going to be equal to 0, which is what we're looking at here when it comes back down to ground level. If there was a ground there, whereas, we're actually hitting it off a cliff. That's either going to be when x is equal to 0, or when we've got that tan theta is equal to gx over 2v squared cos squared theta. So we've got all of that, which means that x is going to be equal to 2v squared sine theta cos theta, because one of the cos is going to cancel, divided by g, which is a double angle. It's what's that, cos 2 theta, so sine 2 theta, v squared sine 2 theta over g. So if we've got two angles that are fitting in here, so if we've got sine of 2 lots of 5 degrees is sine of 10 degrees, and that equals sine of 2 lots of 85 degrees, which is 170 degrees, because that's how sine works. So they are both going to hit at the same x value. So that's why they go through that same point. I doubt, for how many marks was that bit? For 2 marks, that they'll be expecting you to do that. I mean, you may have a hunch that they're going to go through there, but anyway. B, using separate axes, now sketch the absolute distance, a Pythagoras type approach, from its launch point as a function of time for all 3 launch angles. Right, so we're turning this into absolute distance. So this means we're only going to need positive on this. So this is going to be against time, isn't it? So we've got time, we've got r. So let's think of what's happening for each one of them. So when we've got, so let's take the 5 degree one, it's the flatter one, so it's probably going to be a bit easier to describe, maybe, I don't know. When we start off though, it's moving directly away from the point where we started. It's then going to slow down a little bit because we're chucking it up in the air. Then it's going to come back. When it gets back to the same height as where it started, it's now moving at an angle which isn't directly away. It's not radially moving away from the starting point now. It's got a tangential element on it. So it's moving slower relative to the starting point here than it was at the beginning. So we're going to get initially a quick change in our relative distance, our absolute distance. Then it's going to slow because we're losing energy, or kinetic energy anyway. Then it will speed up a bit, but not as well. I say it's going to speed up a bit. I mean, where does it start speeding up a bit? It's slowing because it's got to be slower here because it's now moving tangentially at least a bit compared to where it started. But then we're picking up a lot more kinetic energy because we're getting that conversion from the potential energy. So it's going to start quickly, slow down, and then it's going to speed up again. So we're going to get a shape like that. So that's going to be, let's say we've got that sort of thing going on, and it's going to be getting quicker and quicker. So let's say that's the 5 degree one. So what's the difference going to be then for 45 degrees? It's starting off more or less the same, but it's going to slow down more. You're going to get a bigger, it's going to be going slower here than it is for the 5 degree one. And then here we're going even more tangentially than we were for the 5 degree one. So we're getting a bigger drop off than we did for the other one. And then it will then start accelerating again. And then we've got an even more extreme version for the 85 degree one. So we're going to have something like that for 5 degrees. It's got to start off initially the same. And then we're going to get a bigger change for the 45 degree ones. And then the 85 degree one will be doing something like that because we are going to be closer here than we were when we were here. So at least the 45 degree one is always getting further away. It's not going to be any point where it's coming back closer again to where we started. So, but actually it's going to go, is it going to go flat? You would have thought that's going to be the changing point then, that we're going to have a flat bit in here and then back up. So, because then that's making that transition between the 5 degree where it's always getting further away, the 85 degrees where it's coming back a bit closer and then going further away again. So the 45 degree one, you would think through symmetry, is going to be the dividing line between those two sort of domains. So yes, and then of course if we add 90 degrees, it's going to go out and then back and then off again. So it's going to, yeah, that would work, because if it was 90 degrees, it would do something like out and then back to where it started and then off. So you're going to have that sort of approach where we're actually going to touch, but we don't need that line on there because I haven't asked about that. Oh, this is a lot of work. We've only done 4 marks of a 10-mark question. Obtain an expression for r as a function of time for which angles does r of t have a stationary point. Right, so this is now going to say then whether that is actually flat or not. I mean, maybe it isn't going to be flat in there. Maybe there's going to be some other point. This is where we're going to find the moment of truth on this line as to whether it's just always going up or whether it's going to go flat. So, you know, we've got a potential hunch going on, but it was nothing more than a hunch in part B. We'll find out what's going on here in part C. So what are we doing again? Obtain an expression for r as a function of time. All right, we can do that. For which angles does it have a stationary point? Right, so we can use this thing. Which bit are we going to use? We're going to use, well, we can use these bits. So yeah, let's just put all of that in. I mean, I know what these things look like. I've written this sort of stuff out before. So let's go to a whole blank page. So r, because we're just doing Pythagoras on x and y. So it's going to be the square root. So we'll have big brackets, put the square root in outside there. So that's t squared v squared cos squared theta. And then we're going to have, so we want all of this squared. So we're doing ut plus a half at squared. So let's put the t in. So it's v sine theta, that's our ut, minus gt squared over 2. So that's that. So, and we want to get stationary points of this in time. Wowzers. Okay, so r dot is going to be, good grief. So it's going to be everything in that bracket. So I'm not writing it out again, to minus a half, multiplied by a half, and then we need to multiply by the derivative here. So that would be 2t v squared cos squared theta, right? And then we've got this bit, which is going to be, oh my word, so 2 times that bracket, so the TV sine theta minus all of that, then multiplied again by the derivative of that, which would be v sine theta minus gt. So in here, we've got that bit, okay? And in here, we've got everything in the big bracket up the top, so all of that stuff. And we want that to be, yeah, that to be 0. Well, the first bracket can't be 0. So if r dot is equal to 0, because we've got something squared here and something squared there, so that can't be 0. So that is not 0. So we need the second bracket to be equal to 0. So we need then that is equal to 0. So that's what we've got to work out on all of this. So let's write this out again. 2t v squared cos squared theta plus, where was I? Right, I need to now see what all of this is. This is going to be, right, let's write this out in 2 bits. So we've got 2t v sine theta minus gt squared times v sine theta minus gt. That's got to be equal to 0. Right, so let's expand out some more stuff. There's nothing I can like divide through by here, is there? No. Right, 2t v squared cos squared theta plus 2t v squared, oh nice, yep, sine squared theta, right, so that's helped, minus 2t squared vg sine theta minus gt squared v sine theta, and then plus g squared t cubed equals 0. Right, so we can get rid of that and all of that, because that's a sine squared plus cos squared is equal to 1. That's good. If we got any, these things are the same. Are these the same? We got a, I've written all my letters in different orders. So we got a v t squared g sine theta, v t squared g sine theta. So that's -3 lots of those. Right, let's scroll down again then. So that's left us with 2t v squared minus 3 t squared vg sine theta plus g squared t cubed equals 0. Right, and I can't even remember what I'm trying to work out here. We need real solutions of this, don't we? This is what we want. We want this to have solutions. We've got a lot of t's here. So we've got one potential solution is t is equal to 0. Don't really know what that means. So what would that represent? If t is equal to 0, then if t is equal to 0, then r is nothing's moving. I think that's what we're saying, isn't it? I don't really know what that means, but it can't be the solution. It doesn't. Right, so let's get rid of that. Put this into a quadratic. I'm going to maybe come back to that t is 0. So let's put it into a quadratic in t. Minus 3t vg sine theta. And then what would that be? Plus 2v squared equals 0. So we need real solutions for, so our b squared, which is 3vg sine theta squared minus 4ac. So that's 4, so that would be an 8, v squared g squared. Has to be greater than or equal to 0. My word. That is then, what am I going to be able to do with this? Oh, we can get rid of the g squareds. They can all go, and the v squareds. That helps, doesn't it? So 9 sine squared theta. Well, actually, why am I'm only going to end up square rooting it again if I do that, aren't I? So we need sine theta to be greater than or equal to, square root of 8 is 2 root 2 divided by square root, well, divided by 3. Right, so we need all of that. Well, that isn't going to be 45, so my hunch failed then. Let's stick that into the calculator. So theta is going to be 70.52878 degrees. So theta greater than 70.5 degrees. Right, so is that what I wanted? What was that t is 0 thing then? So for t is 0, that means we've got the, well, just nothing's doing anything. It seems like a weird, yeah, there's like time's in standstill. It's a strange one, but anyway, so that's for what angles does r of t have a stationary point? Yeah, so we've now, that means when we were drawing this graph, then we do want the 45-degree graph to be going upwards all the time. And then 85, yeah, it does fit with our picture. So now our new picture then, if we were going to go back to this one again, r and t, the 5-degree one doesn't have much curve in it. The 45-degree one has got a bit more curve in it. The 85-degree one, we now has got that going on with it because it's above that 70.5 degrees. Excellent. For angles below these, what happens to r of t as time increases? Well, it just always increases. It's always going to be going upwards. I think that's all we can really say about it, because there's never going to be a stationary point. It's just always increasing. Right. And I mean, it's going to increase at different rates, but it's always going upwards. Right, that was another really nice question. I mean, that's a lot of work for 10 marks. That was a very long question, but it was a nice one. So, but I do like projectiles, so there you go. But I'm going to have to leave this video here, I think. I've only done 3 questions, but they were quite long ones. So that's the second bit done.